So we've talked about circular motion when the path is horizontal. So it's on the horizontal plane. You imagine like a flat table, and maybe something turn around in a circular path on that table, or maybe say there's a planet going around like a star. We can imagine that as being flat. But there's also a lot of cases where the circular path will not be in the horizontal plane. One of the most common examples that you might have experience with this is if you're on a roller coaster, you see the whole loop-to-loop thing. That's the plane of that circle is actually in the vertical plane rather than the horizontal plane. This also occurs if you have, say, a car going over a hill or at the bottom of the hill going back up. These are also vertical circles, and I'll show you that. So what I want to do with this video is I want to show you guys the physics of this, the forces and how we treat the forces acting on it and how we find this centripetal force, because fundamentally the centripetal force is just the net force that's pointing towards the center of the circular path. So let's go ahead and get started. So first we'll consider this case of motion in vertical circles. So say we have maybe a ball attached to a string, and now instead of looking from the top, maybe this is the path. Okay, so you'll twirl this ball around in a circular path. Okay, and we'll consider the case where the ball's at the top of the path and the case where the ball's at the bottom of the path. So at the top of the path, what we can you can imagine the forces acting on it. When we do a free body diagram, we'll have the tension of the string acting on it down, and we also have the force of gravity acting downward on it. So the tension of the string and the force of gravity are both pointing in the same direction. Now if this ball is at the bottom of the curve, we still have gravity, the force of gravity pointing down, but then we'll have the tension of the string pulling up. And so the point I want to make is that when we have this situation, these two forces, both the top and the bottom, they'll combine together in order to provide the centripetal force. So when we're at the top, what we can say is, at the top here, what we can say is that since we're going in the same direction, the tension plus Fg, they both point down, they both point towards the center of the circle. So the combination of the two will have to be equal to the centripetal force, which is mv squared over r, where r is the radius of the circle. Okay, so an interesting thing here is you can imagine that this force of gravity will always be equal to mg. That can't change. The thing that can change is this tension. Okay, so we'll have this tension force. The tension plus mg is equal to mv squared over r. Now I want you guys to think of this. If the velocity is high, okay, so at high velocity, both tension and this force of gravity are needed to provide the centripetal force. So needed to provide enough centripetal force, okay? But at low velocity, the tension is going to get less and less and less. Again, we have mg, which is mg. It's not going to change. And so as this v goes down, and as we need less and less centripetal force, what's going to happen is this tension is going to go down. And the tension is going to decrease, 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 until eventually it reaches zero. And eventually there will be some minimum velocity. So the minimum velocity, and minimum velocity, and at that minimum velocity, mg will be exactly equal to what is needed to make it go around in a circle. So this minimum velocity, this is the minimum velocity you need to make this ball go around in a vertical circle without it like falling down towards the ground. This also theoretically, in the absence of friction, would be the minimum velocity you would need, say, for a roller coaster to go all the way through the loop-to-loop, okay, without falling off the track. Okay. Now, if you get below this minimum velocity, what's going to happen is mg, again, is going to stay what it is. It's going to be what it is. So if v is too small, then that means that the force of gravity is greater than what would be needed to make it go in a circular path, and the ball will start to fall down. Okay, so that's what's going to happen at the top. And then at the bottom of the circular path, we have T, and I'm gonna set T as being positive because, again, our net force, if this is going to go in a circle, our net force has to point towards the center. So it's going to be T minus mg, and that's going to be equal to mv squared over r. Okay, so what we have here is this tension. Okay, it has to be equal to the weight plus mv squared over r. So when we have an object going in a vertical circle and it's at the bottom, the tension of the string will no longer be equal to the weight of the object. It's going to be the weight of the object, because it's got to, essentially counteract gravity, plus it has to add a little bit more to provide a centripetal force to make it go around in a circle. So these are the two types of situations that you'll see with vertical circles. Now, a variation on this, so this is where we have a string pointing towards the inside. A variation of this could be a car going over a hill, Okay. So if the car is going over the hill, okay, the circle, essentially, this hill will be part of the circle. We have the car going over maybe the top of the circle, okay, R. And when it's at the very top, and when you look at the forces that we have present, we have mg, this force of gravity, and then we have the normal force of the road. Okay, so if you think about the centripetal force in this case, okay, the centripetal force, again, the net force pointing towards the center of the circle. So in this case, we'll have mg minus Fn has to be equal to mv squared over r. Okay. And, this mg will be equal to mv squared over r minus Fn. So, okay, now get this. If the velocity is low, mg is going to be greater than what's needed to make it go in a circle, and so Fn, essentially the road will push up on the car, and if you're in the car, you're going to feel a seat push back up on you. Okay, but as v gets greater and greater and greater, more and more of this force of gravity is going to be acting as the centripetal force that makes it go in a circle, and this Fn is going to get smaller and smaller and smaller. Eventually, you will reach some velocity that's high enough where Fn will be zero. It's essentially the same case as over here. Okay, except now, instead of having a minimum velocity, what we have in this case is the maximum velocity. The maximum velocity that you can have and pass over this hill without the car leaving the road. Okay, if v is too large, if it's above this maximum velocity, then not only will Fn be zero, but mg will no longer be great enough to make it go in the circular path because velocity is too high, and it's going to leave the road. Okay, so that would be motion in vertical circles, and we'll consider both these types of motion in class. Okay, the other type of, and I call this a non-horizontal motion, even though technically speaking, the plane is horizontal. And when we mentioned this class, this is kind of the conical pendulum. So this is the case where we have maybe a ball is swinging, and it's swinging down. Okay, so I'm not very good at drawing 3D circles here. So anyway, it's swinging down. Okay, and it's angled at some angle theta relative to this horizontal circle. Okay, so it's just going around in a circular path. And I just want to go over this again. I know we went over it a little bit in class. I want to go a little bit more, maybe completely. So when we look at this ball in the free body diagram, we have the tension. We have Fg, this force of gravity. And the part of the tension that's going to provide the centripetal force is this part that's pointing towards the center, so which would be Tx. So essentially, so this has an x component, and this has a y component to it. This y component has to be equal to mg, okay, for reasons that we discussed in the last unit. And then this is going to be equal to my centrifugal force. It's going to be mv squared over r, okay? And so that's theta. So what we can say in this case, there's different ways that you can have these problems. I could give you the weight of the ball, the angle. You could know that Ty has to be a certain value, so you can solve for tension Tx. But eventually what you're going to have is you're going to have the tension times the sine of theta, which is what Tx is, has to be equal to mv squared over r. Okay, and so knowing what theta is, knowing what maybe this r is, so this r would be the distance from where the ball is to the center of the circle, you can solve for, say, velocity. If you know the velocity and you know the r, you know the angle, you can solve for the tension. So anyway, this is the conical pendulum problem. This is another kind of set. It's not your typical, strings horizontal. We're on a horizontal surface. Okay, although the plane of the circle is horizontal still, it's a little bit unusual, and so I wanted to show you guys that in this video and show you how the forces all work out. All right, so make sure you got these down in your notes. Make sure you have all these force relationships down in your notes. And then in class, we'll go over problem solving and some conceptual questions involving them. And as always, let me know if you have any questions.